So talking about FSTAR, I'm very pleased to introduce Karthikeyan Bhargavan, our invited speaker today. Karthik is currently Chief Research Scientist at Cryspen, a company he co-founded to develop and commercialize high-assurance crypto software backed by formal proofs. And that's why I'm interested here. That's exactly the kind of developments we'd like to see from the community. And I'm speaking here on behalf of both industry and regulatory bodies. Before that, Karthik was leading the Prosecco team at INRIA in academic research, which developed a number of tools and proven implementations of crypto primitives, crypto protocols, and as part in particular of the Everest project. And you can see all of that in their recent top-last paper, giving a retrospective and perspectives on the Everest project. And I think it's a must-read for everyone in this room. So with that, I'll leave it to Karthik to dazzle you.
Thank you. Sunday morning, it'll be very liberal with people coming in. I think, well, I'm just introducing myself, so it's kind of okay, I think, yeah. So we all have a background, and a lot of us have a background in programming languages and formal verification, but we find ourselves spending a lot of time applying them to cryptographic systems and talking to cryptographers and practitioners. So usually I'm giving these talks in front of cryptographers, practitioners, telling them, hey, you guys should use formal verification, look what we can do. And today I'm going to reverse that. I'm going to tell you guys what we've learned by applying these tools to crypto. And maybe this might point the way towards some interesting research ideas, I don't know, but at least you'll learn what we learned. All right, so when I talk about real-world crypto, basically what I'm saying is the things that we use on a daily basis. So this is my bank website, LCL, and the only reason I am trusted enough to kind of do my banking on it is that if I click on the lock, it tells me what actually it's doing. And what it's doing is it's running a protocol called HTTPS, inside which there is a cryptographic protocol called TLS, which uses some classic crypto constructions implemented by some standardized kind of cryptographic algorithms that are well considered. And in one form or the other, this TLS protocol has been around for 30 years. So it's been highly studied, implemented many times, tested to death with lots of fuzzers and everything. So it's like a critical component of the web, very well studied. So in a way, by now, after 30 years, we should really know how to do it well, how to do it properly. But of course, when we started looking at the protocol, that wasn't the case. So in the 5 years we studied the protocol, there were dozens of attacks, each of which had an acronym, a website, a logo, press releases, and so on. So it was looking like a pretty bad situation. And it wasn't clear why this kind of protocol is so hard to get right in a world where we already knew by this time to verify operating systems and compilers. And if you go deeper into all of those attacks and try to classify them, you'll find that there are kind of three kinds of issues that come up again and again. The first is, well, over 20 years, any system like TLS is going to use a lot of cryptographic algorithms, a lot of options. And some of them are not going to stand the test of time. They're going to be weak by now, right? They were strong in 1994, but they're weak now. And in protocols that have been widely deployed, it's quite hard to remove features. You can add features, but removing features is quite hard because of backwards compatibility. The second category is protocol design flaws, and this is very rare, but when it happens, it's pretty devastating because it means that you have to change the protocol, to go through the standardization body, make new implementations, propagate them everywhere, and so on. So those ones do happen, and some of them are, and some of them, and they can be pretty bad. But the most common issue, of course, like nobody in this room will be surprised, is implementation bugs. Tons and tons of implementation bugs because there are tons and tons of implementations with varying quality. What's interesting also is that a lot of the bugs that I showed you in the previous slide, which kind of deserved an acronym, were a combination of these. So they use a combination of these things in ways that all the tests and fuzzing and everything else that people were doing on TLS could not catch them. It required quite a lot of ingenuity and therefore papers and acronyms to actually find those attacks. But this, because testing fails in the situation, is also where we think is a perfect example for why you can apply formal verification. So there is this whole field that has now come up, which some people call computer-aided cryptography, some people call this high-assurance cryptography, which basically is what you would think. It's basically taking formal verification tools to produce machine-checked proofs for cryptographic designs, cryptographic standards, and implementations. And the key point here is that crypto, like many other systems that we know and rely on, continuously evolves. People keep standardizing new things, implementing new things, optimizing things, trying to do things in new ways, and so on. And so whatever you put in place has to basically stand the test of time. You have to be able to maintain it, keep evolving it as the systems evolve. And there again, I think formal verification, especially of the kind that we all do, has an advantage there. Because once you have done all the work of building a formal proof, hopefully rerunning it as the system evolves is much cheaper than doing a pen and paper or manual proof again and again, right? At least that's the spiel. A lot of the work I'm going to describe today is going to be taking examples from the last 10 years of work, the first 5 years of which was more like in the research phase of Project Everest, like Yannick was mentioning. And yeah, you can go read the paper about that. And in the last few years, I've been working at this company trying to take the ideas that we learned from Project Everest and apply them to new industrial projects, often taking lessons that what didn't work and trying to do it in a better way. So you'll hear of my experiences in both of these. So let's take the first example about crypto. When you say crypto, you typically start at the bottom with cryptographic algorithms, cryptographic libraries. And what are these things? Well, you all are using them. You may not know it. Every single operating system has its own crypto library. Every single web browser has its own crypto library. Most languages now have embedded crypto libraries. Even IoT devices, however tiny they might be, have tiny little crypto libraries running inside them. Okay, and there are a whole bunch of these, right? And they basically form the trusted computing base for the entire cybersecurity ecosystem. Well, that's part of the trusted computing base. And if you go hunting for the vulnerability reports, this is just 2025. I think there were 12 in Wolf SSL, 6 in OpenSSL, and some of the other ones have similar numbers. Some of them don't publish vulnerability reports, so you don't know, but there's a significant number of vulnerabilities in each of these. And they are the kinds of things you would imagine, memory safety bugs, also interesting ones like side channel bugs, and some functional correctness bugs. And when we started this whole project, there was no verified crypto available for people, none of it. Today, the situation is much better. There's a dozen verified crypto libraries which are now available. And this is basically the effort of the last 10 years, okay? And using a wide variety of techniques. And I'll talk about some of them, but there's many, many. And even this year, we expect at least 1 or 2 prominent companies to announce verified crypto libraries. So verified crypto has now become like a thing. Everybody does this, okay? So the good news also is that for any crypto algorithm that you might want to use today, you shouldn't want to use like ancient stuff. Any crypto algorithm that has been standardized you want to use today, there is most likely a verified crypto implementation of it. Probably it's open source in a very liberal license. And it's very fast. You don't have to sacrifice performance. Sometimes, usually, the verified implementations are even faster than the unverified implementations. It's a bit unintuitive, but we'll talk about why. And all the proofs are mechanized. You can rerun them yourself, and they've already been deployed. So if you go to AWS, you use Firefox, you use Chrome, they're already using verified crypto. So that part of it, success. You can almost declare victory there. So let's see what these guys are doing, what we've been doing all these years to make this kind of thing work. At a high level, the verification workflow is nothing. It's almost exactly what you would imagine. We start from a standard. So all of the crypto things that we're talking about are usually standardized, either by the NIST or the IETF. And the standard is a mixture of English and pseudocode, and pseudocode is written in some Python-like language. And then it has a bunch of test vectors. So that's kind of what a standard looks like. Usually it's much bigger than this, but whatever, right? So of course, the first thing you have to do is to write a formal spec for this. And since cryptographic algorithms are really just mathematical functions, often can be written very succinctly, you can write them in any language of your choice, and I don't even have to tell you how. This is what it looks like in F-star. This is what it looks like in EasyCrypt. Some look more imperative, some look more functional, but on the high level, this is just bit string to bit string functions, okay? Anybody can write this in any, you can write it in Lean, Rock, people do all of this stuff. So once you have the formal spec, you're going to write the implementation, right? And this is where, of course, the intelligence comes in, because the implementation often has to be optimized, both for runtime and for memory, depending on what kind of place you're deploying it in. And so people do lots and lots of tricks, okay? In fact, cryptographic algorithms sometimes are the performance bottlenecks in several settings. For example, for web servers, they can be a performance bottleneck. In IoT devices, crypto, in the size of the crypto itself can be a bottleneck for the IoT device. So it's not just, oh, let's optimize this one cool thing. It's actually the central thing that we have to optimize. So people end up writing very optimized implementations for these. So in F star, for example, you write something like that, and it gets compiled into C code. So it looks something like that. So whatever. Or if you want to really, really optimize it and have a lot of control on the low-level implementation, you might write it in a pseudo-assembly language. You can write it in Jasmine or a language called Whale, which we'll talk about later, perhaps. And in this case, you're really writing it like assembly code in a way that can be compiled down to, for example, in this case, this is AVX2 assembly for Intel. So it's really focused on performance, but also on low-level control of what's actually going to happen at runtime. OK, so you've written your optimized implementation. You have your spec. So of course, the question is, how do you verify it? Most of the people in this room should be able to verify these kinds of algorithms. It's not shocking. It's an input-output mathematical function. Implementation show that they have the same behavior, right? So typically, you prove memory safety first, and you prove functional correctness with respect to the spec. There's a little bit of interesting things going on in terms of proving that your code is not exposed to certain categories of side channels. And there, maybe it's a bit different from what we do in normal software verification. But again, we convert it into a verification problem. So let me give you an example on why this is interesting, where the challenges come from, and so on. So a central, before the post-quantum transition became such a big thing, everybody was using elliptic curve cryptography, which centrally uses a construction called Diffie-Hellman. And if you think of Diffie-Hellman in the school book sense, it's basically something like this. You're doing exponentiation modulo some prime. Okay? And so the central computation there is modular multiplication. A times B modulo some prime P. This is field arithmetic. Okay? So prime field arithmetic, implementing using modular multiplication. Often this one operation, modular multiplication, can be the complete performance bottleneck for a server or for an IoT device. Okay? This one operation. So this really requires a lot of attention, and therefore people optimize the hell out of this. And why? Well, let's go back to school. How does multiplication work? Well, if you do bitwise multiplication, it's basically something like this, right? This is classic textbook multiplication. And if you're doing it with 256 bits instead of 4-bit numbers, it basically is something like this. You divide it up into 64-bit components, because that's the word size on your machine, most likely. You multiply it, and you get 128-bit values for each of these ones, and you do some carryover, and you carry over. You do all the additions and so on until you get the full value. And when you get the full value, you have to do the modulo P. And so you do a reduction steps. It brings you back into a much smaller result. Okay? So, and you basically, every multiplication is something like this: multiply, carry, add, reduce. And if you always did all the reduces, and if you always did all the carries, because there is a chain of things which cannot be parallelized, this thing ends up being quite slow. So all the tricks for optimizing this are in trying to parallelize as much as you can the additions, the carries, and the delaying the reduction as late as you can. Like if maybe I can do 5 additions and the thing won't overflow, and then I can reduce it rather than reducing it every time. And each of those optimizations can gain you like 3%, 5%, 10% performance improvement, which translates to millions of dollars for AWS and Google and so on. But then, of course, when you're trying to optimize this, you end up with bugs. So these are all bugs that people have found in exactly these kinds of implementations, modular multiplication, et cetera. So most common one, actually, what happens is integer overflow. So there was some carry you were supposed to do somewhere, and you forgot to do that carry. And now, when you do an addition by 1 or whatever, the thing is going to overflow the 64-bit value. So if you overflow it, on some languages, this is a runtime error. This undefined behavior, runtime error, it might crash. But almost all situations, it's not going to crash. It's just going to roll over. It's just going to wrap around. So you're going to get a wrong result. Okay? But the wrong result is going to happen with very low probability. Right? It's only going to happen when you are really overflowing that particular integer. So a lot of tests could pass. And there might be one test every once in a while that might fail. And if you rerun them in a randomized way, again, it might pass. So testing was very unlikely to find these kinds of little carry failures, which are only going to happen with low probability. Of course, there's also arrays here. So there's buffer overflow, underflow, and there could be side channel attacks. These are all low probability attacks, which testing doesn't usually find. So what is the side channel attack that we might be worried about? So again, a very simplified view of it. So suppose you were trying to multiply these guys. You would basically multiply 0, multiply 1, multiply 0, multiply 1, and you get this result. But looking at this, you might say, you know what? These 0 steps are completely redundant. I can maybe just completely skip them. So if the value is 0, I just kind of skip it, and I just keep going, just shift left and add. Okay? And if this means that at every point you're testing whether or not the value here is 0 or 1 and doing something special. Now, this is a trivial case, but of course, you can imagine optimizations like this. Now, this does make the code faster, actually. Not twice as fast, but 1.5 times as fast. But it leaks information, because now the runtime of this is telling you how many 1s there are in the second argument. And a priori, you might say, nah, the number of 1s may not give me that much information. But if you are able to repeat this, you can actually recover an entire secret key. So there's a whole bunch of papers where people take a 1-bit leak somewhere, and they can expand it out into a leak of an entire secret key. So this is the kind of side channel attack that you want to avoid. So however many optimizations you're doing, you cannot do optimizations that depend on the value of a secret. If your optimization is secret dependent in any way, you're most likely in trouble. There are other ways you could be in trouble too. This is not the only way, but that's definitely one of the predominant ways in which people introduce side channel attacks. So how do we implement and verify that our implementation of modular multiplication is correct? So you can go look at the Hacklestar repository, which shows you one way of doing it. So in Hacklestar, there is what we do is we write implementations of crypto algorithms in F-star, actually in a subset of F-star that's called low star. If you want even better performance and want to write things in assembly, you can write the code in Veil as well, and that's its own project. And both of these could meet the same low star interface. So that's the low star interface for modular multiplication. So what this says is that there's basically an output buffer. These are the two input values we're going to multiply. The prime is already known, so you can ignore where the prime is. This is just a temporary scratch buffer we're going to use. And it's going to basically put the output over there. That's going to have the output. So in order to verify this code, we need a bunch of preconditions. These are all the memory safety preconditions that says which pointers are live. All the pointers must be live, which means they must have been allocated. They must have the length that we think they have in the current heap. And they all must be mutually disjoint. Well, you can be a little bit looser here. They don't actually have to be all mutually disjoint, but this is a simplification. So they all the buffers have to be mutually disjoint. So they should never even overlap, okay? They could be like completely separate. And in that case, we want to prove that, in fact, the output only modifies out and the scratch. It doesn't touch F1 and F2. That's that condition. And this is the functional correctness guarantee, which says that the output, if you evaluate the integer which is stored in the output, it is basically the integer stored in the two inputs multiplied modulo p. So that's what the spec says. So the spec says basically this is the mathematical input-output behavior of this function. So this is your full spec of what modular multiplication should be doing in low star. And we have two implementations of it that we prove actually meets the spec. Okay, actually, we have three implementations. But okay, and those implementations do all kinds of optimizations. One of them is in assembly, right? And one of them is in C, but still is trying to do things as fast as possible. So looking at this, you can already tell where the burden of annotation and the burden of proofs are, even if I have not shown you how the proof works. You can see that the memory safety annotations are kind of annoyingly big, right? But okay, but following that, with a lot of blood, sweat, and tears, we built an entire library with a whole bunch of algorithms, pretty much every modern algorithm that you want. Okay, so it's not just a demonstrator on one algorithm. No, it's like all the algorithms that people use in TLS were written, verified in low star, some of them in Veil, optimized as much as possible, some of them with SIMD optimizations for different platforms, everything verified. Okay, and that generates code. It's written in F star, verified in written in low star, verified in F star, and it generates C code, and today it also generates Rust code. And it's widely deployed. But the effort is huge. So it's 250,000 lines of F star, which generates about 130 lines or 30,000 lines of C and assembly. And it burnt 3 PhDs, I would say, or maybe a bit more. And I do use the word burnt kind of, none of them is in research anymore. And a lot of the effort there was not just building the proofs, because building the proofs the first time around was easy. Well, systematic, not easy. But actually, you have to maintain the proofs as F star evolves, as Z3 versions change. If a proof is flaky on one place or another place, so somebody says, oh, we have to run this on Spark, so you have to add this one implementation detail somewhere and then re-verify everything. And that proof maintenance is actually both psychologically and physically quite a lot of work, at least for researchers who are, we have published the paper. Why are we still taking care of this library which is 10 years old, right? So, but OK, success, let's say. Lessons, well, also because we did a lot of work on trying to deploy this code in real world places like NSS and Firefox and other places, we learned quite a few things. Like, first of all, you can't just say, hey, this is verified, take it. They'll ask you what the performance is. And if the performance is 5% slower than what they have currently, they're not going to take it. Nobody's going to use it, right? So it must match the unverified code. If you can exceed the unverified code, you have an excellent argument. And in some cases, you can. Because like I said, you want to try to delay the reduction, avoid the carries, parallelize things. There are many places in this kind of code where you go and look at it, and there would be a comment by the developer saying, I think this particular carry is not needed, but I'm not sure, so I'm going to leave it in. Because it's always OK to do a conservative operation like that, but maybe it wasn't needed. But if you have verification, you can sometimes prove, in fact, that particular carry or that particular reduction was not needed and eliminated, and now you're still safe, but you're faster. So this is why a lot of verified code, not just in Hacklestar, but also in Jasmine, also in Whale, is sometimes faster than the unverified code it was inspired by. Because with verification, you can actually show that certain operations were not needed and remove them. The other requirement is that your code that you produce, because in our case, we and most of the people in this field are not directly verifying code that users wrote. We write code and we generate C, we generate assembly. And we say, hey, please use this assembly in Chrome or in Firefox or the C. So when you're giving people this code, they, of course, like the fact that it's formally verified, but they don't understand formal verification or what the source code. They're not going to read the F star. They're not going to read the coq. What they're going to read is the output, which is the C of the assembly. So it has to be reviewable. It has to be well commented, has to have nice variable names, has to have the right structure in a way that they can review it as if a human wrote it. Okay? So that actually creates a lot of pressure on the tooling to actually produce code that is actually readable, because, of course, it's much easier to produce code that is correct but not readable. And the other place where a lot of requirements come in from the industrial side is that you might say, hey, I've done the RFC, I'm done, I'm gone. But in fact, the way people use cryptographic algorithms, they use a lot of flexible APIs, and they want to run it on many more platforms than you might have tested it on. So there's a lot of work that is around the cryptography, which is kind of at the edges, in the interfaces, which is actually needed before this can be deployed. And on the crypto proof side of things, well, as I showed you in that thing, the memory safety annotations kind of dominate the specification effort. Proving them usually is quite easy, especially since you're using F star, which is an SMT solver, which is particularly good at proving the kind of memory safety preconditions that we need to prove. But still, it takes a lot of manual work to actually document all of these things. And SMT automation is crucial, but except when it isn't, right? So the Everest retrospective has some nice discussion on this. We find that there's most proofs that we send to SMT are done in milliseconds. But there's a few proofs that might take hours. And so the cost of a verification run is dominated by a few fragile proofs, which you can rewrite in a way that the SMT solver will like. But if you don't do that, if you don't garden those things well, in fact, most of the time you're spending just fixing these 5 proofs that keep breaking every time. OK, so taking the lesson from that, we don't do that anymore. So in Cryspen, we don't actually write F star. We write all our crypto now in Rust, and we verify it from Rust. Okay? We still use F star, but we only use F star as a proof backend. We don't use it as a programming language. And this is primarily so that the artifact that we are verifying is an artifact that crypto developers can write. And even if they don't want to write all the proofs, they can read, right? So that's kind of particularly important. So the example here is post-quantum crypto. So that was our excuse for doing this. So there's a new set of algorithms that everybody is implementing now, and we implemented one of them. We have this tool chain called Hacks, which takes Rust code and then compiles it to F star. Okay? So you can do the same kind of thing that you were doing in Hackle Star, have a spec in F star, derive the F star model from Rust, have a spec for all the Rust libraries that you're using, throw it to F star, try to prove that it's correct, and then use it. Notably, since Rust is already giving us memory safety guarantees via the borrow checker, we translate it into purely functional F star. So we throw out all the memory safety preconditions, postconditions. We say we are trusting that the Rust type checker and borrow checker are making sure that things are memory safe. We don't have to do that. We only have to talk about runtime safety conditions and correctness, and that big simplification. Of course, most people don't still want to use Rust. I don't know why, but there are people who can't use Rust in their systems. And so to support them, we do have a tool called Eurydice by Jonathan Protsenko that takes that Rust code and compiles it to C code. It's kind of weird, but we do it because it's easy for people to use it, whatever. So what does this look like? Well, if you write a reduction algorithm in Rust, this is actually a very simple reduction function. It's called Barrett reduce. It's used in post-quantum crypto a lot, where you take an signed 32-bit integer, and you're basically doing the modulus of that integer with this field modulus, which is the number 3329, a very small number. But you can't just call the modulus function, because that's not constant time. So calling a modulus function on most platforms will leak the argument. And this is a secret. You don't want to leak that secret. So instead of doing modulus in like a sane person would, you actually do all kinds of shifts and multiplications and additions that you know are constant time on most platforms. And this is how these things are usually implemented. So this is actually just you could do one mod, but you can actually do this like this. So what can go wrong here? Well, we said Rust is memory safe, right? So it can't really throw a sig fault, but it can have runtime errors. So that multiplication, that addition, that subtraction, that multiplication could overflow. So and in Rust, those operations in debug mode, if you run them with very large values of the input value, it will basically throw a panic, okay? At runtime, it won't throw a panic. It will just do the wrapping operation, give you the wrong result. But either way, both of them are bad, right? So you do want them to panic if they're panicking. So you want to prove that these things will never overflow, okay? Because that's the intention of those functions. The other thing that you want to ask is whether it's producing the right result. So for both of them, what we do is we add contracts to the Rust program in Rust. So the requires basically says that as long as the value is between this negative number and this positive number, when you're doing signed arithmetic, it's all very kind of interesting. You have to always think about the negative and the positive. Then we can guarantee that the result will be between the minus field modulus and the plus field modulus. And the result modulo field modulus is in fact the same as the input value modulo field modulus. So this is a spec of Barrett reduction. So this is the functional correctness spec, and this bit is what you need for panic freedom. So under these conditions, you take that code, translate it to F star, and say, hey, can you prove to me that none of the arithmetic will ever overflow? And can you prove to me that this post condition holds? The SMT solver is able to prove it completely automatically without any annotations. Okay, so for 32-bit integers, there is enough information in the SMT that it can actually do this automatically. We also did these kinds of proofs manually in Rock, in Lean, and so on, and it can sometimes take hundreds of lines of proof. So this is a classic place where SMT is doing the right thing. Of course, it's very fragile, so a small change and maybe it's not going to do the right thing. Then there is secret independence. So we want to prove that, in fact, none of the operations is going to leak secrets. So we kind of have a notion of secret integers on which you're only allowed to do certain kinds of operations and other operations are forbidden. And that basically prevents a lot of the leaks that can happen at the source code level. But note that we are at the source code level. We don't know what's going to happen at the final target code level. But even so, at the source code level, we can find attacks. So while verifying our Rust implementation, we found a place where we were doing a modulus operation, actually a division with a constant. And on the left-hand side of the division, there was a value t, and the value t was a secret. We're saying we're doing secret divided by something. And according to our rules of secret independence, this might leak the value of the secret. So we fixed that, and then we went and looked at the other implementations, including the reference implementation of the standard. And in fact, the reference implementation had the same issue. So this, then some other colleagues of ours showed that this bug can be expanded out into a big attack, and that became known as the Kyber slash attack. And that's kind of, that was a paper at Chess this year, won a Best Paper Award and so on. All we did was to run our tool to say that there is a bug in our code, and this bug seems to be in other code. All the rest of the work, which is really hard, is done by the cryptographers. But this shows that already with these kinds of type-based analyses at the source level, we can find interesting things. We just said we can't be sure we have found all the things. So libcrux exists. You can go try it out. It has optimized portable implementations of MLChem and MLDSA. It also has Rust implementations compiled from Hacklestar for all the other algorithms you looked at earlier. So it's a pure Rust crypto library with decent performance, I would say. And it's already deployed in Firefox and Signal and so on. What lessons can we take? We're still not done with crypto, but I would say crypto verification is kind of almost a solved problem, as in it won't be surprising if you tell somebody, hey, I verified this new algorithm. That shouldn't be surprising anymore, but there's still interesting questions left which are open. The first thing is side channel analysis. So we are doing some very weak side channel analysis at the Rust level, but really between Rust and the time when it's actually getting executed, there's a whole bunch of side channels that might be introduced. The compiler itself might introduce some side channels. Plus, there could be speculative execution problems at the microarchitecture level after even we get to assembly. To address this, we need very precise machine models. We need specialized tools. We might need support from the compiler on how to compile crypto code and so on. So it's an open question. Lots of people are working on it, thinking about it. There's a whole session on it today as well in one of the other conferences, I think. And so this is an interesting but open area. Of course, there is the alternative, which is write everything in assembly. And for some people, that is actually the right solution, because they really care about crypto. They want to write all their crypto in assembly and verify it in assembly, so they have full control about where things are, and they can run a lot of tools directly on the assembly code. I find that depressing, because it's been so long that we've tried to build these compilers, and now to say, all right, maybe AI will make that easier. The other thing I think is that anything that you do like this has to fit into the developer workflow, right? So, I mean, we can write code, yes, sure, but we shouldn't be the people to write crypto code. We are like formal verification people. The crypto developer should write the crypto code, and we've had trouble getting them to write things in C, even in F#, F star, Coq, that in a way that can be verified. With Rust or domain-specific languages like Jasmine and Whale, there's a better chance. The people that crypto developers are willing to write and use these nice new modern languages to write their code in a way that can be verified. And of course, the last thing is that verification still obviously is only one component in the larger ecosystem here, because there are a lot of edge cases to the verification where we are not proving things, and we need testing and fuzzing to fight those things. All right, so we talked about crypto, but really a lot of the interesting things are at the protocol layer. So we talked about TLS and said, oh, there are so many attacks on it. So there was this whole effort on standardizing TLS 1.3, where the entire community came together and they said, hey, you know what? We're not going to standardize this new protocol until the academic community comes and does proofs and tells us that this is actually secure. So a lot of these proofs are pen and paper proofs, the ones in black, but the ones in green are actually machine check proofs that people did. And they were highly regarded. So people were waiting for the machine check proofs before they standardized the protocol. So in a way, this was kind of successful. The ones in red are the ones where actually important attacks were found on the protocol and then fixed. So obviously, the latest ones hopefully did not have any attacks. And so this was like the most analyzed protocol ever. And this is basically a complex-ish protocol, but still fits on one page. So it's not terribly difficult, but still it was quite a lot of work. And in our group, in Project Everest, we developed this implementation called MeTLS, which over time covered many different modes of TLS 1.0, 1.1, 1.2, and 1.3. And it's a pretty large project. It lots and lots of modules. It models all the state machines, also precisely implements all the message formats. It's a reference implementation, so it has to be interoperable with other implementations of TLS. Use verified crypto, like we talked about from Hacklestar and Whale. And it's a major effort with lots and lots of researchers, more than 30,000 lines of protocol code in over 100 modules. And what's interesting, perhaps, is that when you talk about protocols, unlike cryptographic algorithms, which are mathematical functions, so the specs can be very succinct, when you come to a protocol, like I showed you in the previous slide, the spec of the protocol can itself be very large. I mean, almost as large as the implementation. So in some cases, a reference implementation is as good as the formal specification. If you write it in the right language and so on. And let's forget about C, but if you can write a reference implementation of TLS or MLS or Signal in Lean or whatever language you like, it probably serves as a good spec. Okay. But this is big, so the implementation is big. The nice thing is it helped us find attacks, and while developing this and while verifying it, we found quite prominent attacks, and it influenced the design of TLS-1.3, but it was a lot of work. What we learned from it was that, well, you can't just focus on the crypto, because a lot of the issues, verification issues, as well as bugs, as well as things that people actually care about, are outside the crypto. They are in protocol message formats, they are in state machines, they are in things which are classic software verification things, but interacting with crypto in interesting ways. In particular, there are things like downgrade attacks that only appear if you model two different versions of the protocol and enable them both. Then you have to worry about how they interact with each other. If you verify just them in isolation, you would not see these attacks at all. So the more you can put into your implementation, the more attacks you'll find. And verifying a reference implementation is a way to ensure that we captured all the details. The other thing we found is that when we were trying to do monolithic, all-in-one proofs of security, correctness, memory safety, all in F star in the same model over the same artifact at the same time. And this was okay for small protocols. At the level of TLS, it was not scaling. It just wasn't. It just took us way too long. We never finished the full proof for the whole thing. I would say that part of it was a failure. And while doing this, we discovered that, well, there were different ways of doing proofs for the different things that were working. So for memory safety in low star, that was kind of working. The annotations were big, but it worked. It was quite easy to automate. For cryptographic security, a whole new technique called state separating proofs was developed, which was then embedded into F star, but also had its own tool called SSProof. For parsing correctness, a whole new tool called EverParse was developed. And these are all different ways of verifying different parts of the problem. They were all embedded in F star in a way that they could talk to each other, but they were kind of completely different verification techniques. So taking those lessons to heart, we don't do that anymore. So at Cryspen, we recently built a TLS implementation just as a demonstrator at CCS this year called BERTI. And it's a post-quantum version of TLS, so it's TLS plus also some post-quantum cipher suits, and it's open source. You can go download it and whatnot. And when verifying BERTI, we now use the HACS methodology again. We take the Rust code for BERTI, we take HACS, and for certain modules, we produce F star. For certain modules, we go to SSProof for the cryptographic core. For certain modules, like the protocol modules, we go to ProVerif. And we prove different properties for each of these. For some modules, we actually analyze them in two different ways using two different tools. And of course, the crypto itself comes from libcrox, which is formally verified, so it's on the side. Okay, so these are three completely different techniques for verifying different kinds of properties. In fact, not just that. So we use the Rust type system to enforce state machine linearity, and we use all of these different things. And we were able to do this entire work in about a year, including the implementation, including all of these other proofs, and so on. So we felt that that was the right level of effort for this kind of project. This is not as comprehensive a result as you can get for MeTLS. It's not all in one. These are completely different proofs. There's no single formalization linking them all. So there are weaknesses. But pragmatically, we were able to prove a lot more of the properties we cared about using that methodology than if you went for a single unified one. All right, so the last part of my talk is basically saying, well, what does all of this mean for future protocols, right? So what if some company comes to us and says, and this is what people do with Cryspen, and says, hey, we have this completely new protocol we want to deploy. Can you help us formally verify it? Okay. So in this world, I'm going to take the case study of Signal, who we've been working with for the last year. And if you know anything about how the Signal protocol works, whenever you open a new Signal conversation with somebody whom you have never talked to before, by the way, Signal is the same protocol is used also on WhatsApp and Facebook Messenger and so on. Okay, so it's the same protocol, but I'm talking primarily about the Signal messenger here. So when you want to send the first message, it does this protocol called X3DH. What it means is that you're going to take your key and the other person's keys, and you're going to mix them with like 4 different Diffie-Hellman computations and get a key. And once you have started conversing with each other, with every message, you're going to refresh the key. And this is called a double ratchet. Okay? And this kind of protocol is state of the art. I think people strongly believe that this is the right way to do messaging. This is why WhatsApp uses it, Facebook uses it, and Skype, when it existed, used to use it. And it gives you very strong guarantees. So some of the strongest guarantees, even stronger than TLS, because it gives you post-compromise security, which is that if somebody takes away your phone and then gives it back to you, and you continue your conversation, within a few messages, you will recover your security, even though that person who took your phone has learned the messages they learned at that time. They cannot interfere beyond the time when you got your phone back. So this is kind of important for many kind of whistleblowing type situations. There's also like some effort at providing deniability. I don't particularly believe that that's a very useful guarantee there, but let's ignore that. So that's the classic protocol. So last year, 2024, Signal decided that they wanted to make their protocol post-quantum secure. And post-quantum secure in a particular sense, that if somebody were to download all the Signal messages sent from anybody to anybody today and store it, and waited 10 years until a quantum computer came along, and then they tried to decrypt everything, they shouldn't be able to get all these messages. Okay? With classical Signal, they can. So you store all the messages from Signal server 10 years from now, if you believe that a quantum computer is coming in 10 years from now. It's up in the air. You will be able to decrypt all of those messages. And some of these messages may still be sensitive 10 years from now. So, but to avoid that, what you can do is you're already doing the 4 Diffie-Hellmans. Keep them, because that works. Everybody likes that. Let's add a post-quantum crypto construction in here. So now we have these 5 secrets. Earlier we had these 4 secrets. Now we have a 5th secret coming from post-quantum, and mix them all together. So it's purely additional, right? So we had 4 secrets. We're going to add a 5th secret, mix it together, and put it into the protocol. So now we have post-quantum spice on top of our Signal soup. And yeah, so the protocol itself, this is what changes, this changes, but most of the protocol can remain the same. Okay? And this for them was very important, because they really live on their reputation. And their reputation is that their protocol is good, and they don't take influence from any government, and everything is open and transparent, and they can show that, oh, look, we only added some things. So it's a very small edition. It should be very easy to analyze. So they published this spec, and I and my colleagues were like, hey, let's analyze this just as a kind of a weekend project, because we already had models of the old protocol. So we're like, hey, let's model the new protocol. So we want to check that the new protocol is at least as secure as the old one, because it's additive, right? And that it's secure against certain categories of quantum adversaries, because that's the whole point of post-quantum crypto. So what we did was, of course, we wrote down the protocol spec. We added a compromise model, security goals, cryptographic assumptions on what actually we assume about the protocol. And then we ran this tool called ProVerif, which is a domain-specific tool for doing protocol analysis on this protocol specification. And whenever if you found an attack, it could mean that, oh, actually we modeled something wrong, or it could actually mean that the protocol is broken. And once you have found all your bugs, you might then say, hey, you know what, I want to do actual crypto proof, like a pen and paper cryptographer proof. And for that, you can use this tool called Cryptoverif, which uses the same input, but actually can do crypto proofs. That's the idea. If you're curious about what these things look like, the specification of this thing in ProVerif looks something like this. So it's it doesn't matter, but the syntax is not so shocking. The Signal developers were able to read and edit these scripts. Okay. And then if you press a button and say, ask ProVerif, hey, can you prove that this is post-quantum forward secure, this is a query which asks that. It's a very weird syntax, but hey, whatever. You can think of it as like a safety kind of temporal logic type formula. It's called a query in ProVerif. And if it doesn't hold, ProVerif will give you an attack trace. Again, the attack trace takes a little bit of brains to figure out what it's doing. Apparently, Claude is very good at interpreting this and giving you very nice. So we don't need to make better tools anymore. We can just ask AI to explain what the bad results of our tools mean. So it can actually explain to you quite nicely what this means. So I'm not going to even try, because I can't do as well as Claude for this. And once you're done with those, you can actually take the same model and write this is kind of a pen and paper crypto proof. It's called a game-based proof, where you say, I'm going to treat the initial protocol as a game between the attacker and the protocol, and I'm going to describe a set of transformations, which are each of them is justified by some cryptographic assumption, and the final game that you end up with is going to be trivially secure. Okay, so that's kind of the style in which you do these proofs, and this is a cryptoverif proof of that protocol. Again, I'm rushing through this. If you have any questions, I'm happy to answer. Right? So, and then, of course, we want to model a quantum adversary. And, of course, it's hard because the quantum adversary doesn't really exist. So most of us have ideas of what the quantum adversary could potentially do. But every second week, there is a paper that tells us that the quantum adversary's powers might be more or less than what we thought. So it's a very fuzzy area right now. But OK, at least what everybody agrees on is that when the quantum adversary finally appears, Diffie-Hellman is kaput. We can't use Diffie-Hellman anymore. So that's for sure. Everything else is a bit unsure, but OK. And that symmetric crypto is kind of good. Symmetric crypto is good. Diffie-Hellman is bad. That we can agree on, for sure. So for Proverif, that's basically what we do. We basically allow the attacker to break. There's a quantum apocalypse after which it can break all the asymmetric crypto, but not post-quantum crypto. And then Cryptoverif has a special mode to exactly prove properties even under passive quantum adversaries. So we use that. So using that, we can then try to prove the thing. And while proving it, we find a few attacks, bugs, vulnerabilities, attacks. One of them, which is the easiest to explain, is this one. Look, I said we're just going to add this one thing here in the protocol. This one thing is actually signed by B. That's what this curly bracket means. But in the protocol, there was already another key there, which is a Diffie-Hellman key, also signed by B. So, well, what if the attacker took that signature signed key, put it here, this signed key, put it there? Then you, when you are creating a first message with this person, are going to use this one as a post-quantum key, but it's actually a 32-byte Diffie-Hellman key, and this one as that one as a Diffie-Hellman key, which is post-quantum, and this one as a post-quantum key, which is actually a Diffie-Hellman key, and all bets are off. Okay, in reality, one of them is a 32-byte key, and one of them is a 1 kilobyte key. So most implementations will basically crash rather than actually do the computation. But the spec does not say that, in fact, they should all be this size. So it's possible that there is an implementation that will pass this, and then all security bets are off. So this is a classic protocol flaw. Right? This is a confusion formatting flaw, very classic. Lots of people could find this before. And Proverif obviously can find this kind of attack, and found this attack, and found some few other weaknesses. And this is representative of a general class of problems that comes up. And this is the kind of thing that, one takeaway from that is that whenever you have version 1 of a system, tomorrow you're going to have version 2 of the system. They both have to live together, most likely for a long time, but even if not, at least for a month or two. And in that period, you have to be very careful about confusion and cross-protocol attacks between version 1 and version 2. A lot of flaws come from there. And an immediate fix is that make sure that all your formats are very, very explicit and disjoint between these versions. And of course, there are nice frameworks, including the one by my student called Comparse, which can guarantee that you would have this property. So with PQXTH, what happened was our results, we told them, hey, look, there's a bug. They fixed the bug. They pushed out a new specification. We proved that the new specification was we formally verified in both Proverif and Cryptoverif. And they basically said, OK, we're done. And this whole process from the first version, verification, new version, was 1 calendar month. So I think that's kind of, for me, always a big marker of success, that somebody can come, use these tools, and do things in a month. I mean, not somebody, we did, but. So the Signal team was impressed enough that, in fact, for the next protocol that they deployed, which is now in all your phones if you use Signal, which you should, it's called the sparse post-quantum ratchet. It's it was formally verified from the very first moment that they started even sketching it. They verified it in Proverif using some of the models that we provide them. And then as they started implementing it, and it was in parallel, things are never like beautifully phased, right? They started implementing it. They used hacks to verify the code from the very beginning as well. So this is part of their CI. They run it on every check-in. The developers write the annotations. Often they need advice from us because hacks is not such a great and usable tool, but they're nice to us and they kind of tell us when it doesn't work. And so in collaboration, this is actually running right now on Signal CI. This has become part of their workflow. You can read about it in their blog post. And we are basically using the same thing we did for Bertie. We use hacks. We extract F star to do some kinds of proofs. We extract pro over F to do other kinds of proofs. All right, final set of lessons. When interacting with people like people from Signal, who are real developers, crypto designers, and so on, and we want them to use the tool. We don't want to build this whole thing and give it to them because it's their stuff. The choice of programming language and specification language is crucial. So Rust is very attractive to a whole set of programmers. They're much more accessible. But also the specs, if you told them, OK, you can write Rust code, but the specs should be written in this weird custom language, even that's not doable for them. They can't, somehow there's a blockage there. So if you can write your specs also in Rust, good. Or if it's in a special annotation language, you really have to work hard on making that really accessible. Using multiple provers was great for lowering the verification effort. But of course, big caveat, we are not getting an end-to-end security result like we were aiming for with MeTLS and so on. Because these are 3 different tools, 4 different tools. There is nothing formal linking them. Okay, so it's a very pragmatic approach, but not really a foundational or compositional approach. Concluding, I hope I have shown you what exciting things people have been doing with formal verification and real-world crypto. Today, there's verified crypto libraries in all major web browsers, and hopefully soon in all major operating systems, and verified implementations and designs for many prominent protocols. Even Apple's PQ3 has a formal verification in it. It's become kind of default for new protocols, I would say. The next challenge is, but this is all done by, this is all done by people like us, right? We write the stuff and we give it to them. And that works only up to a certain stage. It doesn't really scale. We really need them to use the tools, right? And especially for cryptographic developments. So making that usable is a challenge. Rust and some languages, domain-specific languages, can help bridge the thing, but there's a bunch of open work there. And the last comment I would like to make is that there's this big thing going on right now, which is the post-quantum crypto transition, where everybody is changing their cryptography to be secure against quantum computers. Whether or not you believe in quantum computers or whether this is a good idea or whatever, this is a great opportunity because they're all upgrading. Basically, every crypto stack in every device, every hardware, every software is being upgraded everywhere. I think we should use this as a stealthy moment to push in verification everywhere, right? Even if you don't care about the quantum adversary. And that's what we're trying to do, and I think everybody should be doing this. Anybody says, hey, we want to do quantum, we say, hey, verification. Yeah. So anyway, so that's that, and I'm open for questions.
We have something like 10 minutes for questions, and we have a mic. If you have questions in the audience, because 2 mics even, because we have the recording and the streaming. So please raise your hand for questions.
Hey, very nice talk. You said that nowadays you sort of write your protocols in Rust and then sort of trust the Rust type system to do sort of the right memory safety things and then only verify the rest. But then you also said because people still use C, you have some compilation to C. Which memory safety guarantees for C do you get?
C Lite, which is the internal language of Caramel, which is very similar to C Lite as used in ComSert. And then we use the same Caramel toolchain that we were using in Hackle-Star and F-Star, Low-Star to translate it into C. So, so the argument, and this is informal, is that the Rust code and the C Lite code have the same behavior, even though their memory models are quite different, because we are in a very restricted sublanguage. So we're going from a very restricted sublanguage to a very restricted sublanguage. We're never in full C, actually. We're still in Low-Star, let's say. And so from that point on, we get the formal guarantees of Caramel that were verified in SEFP, whatever. But this first stage,
So you were saying that at the beginning you are doing like proofs, you are taking proofs on models and then you are translating them to code, but then you switched to looking at the code and then translating them to models. And actually, in the end, like you said, that this also has some limitation that, okay, you don't know like what's exactly proved in the end. And actually, indeed, like when you do the translations, like, I don't know, translation to Proverif or to F-star, or like I imagine like those translations are not ideal. Like if you would write directly the model in Proverif, it will write maybe even a more realistic model, because I don't know, in a I don't know, some Proverif experts, they know, okay, this causes problem. So the question is, okay, I don't like, and then I think you also asked the question, but you didn't provide the answer. Like when you have a new protocol, like what is really what should be the workflow? Because for example, if even in Signal, like the protocol changes, do I really need to rerun this, like your tool, the hacks, or like do I need to first maybe rather look if I want Proverif, if the protocol changes, then I do the changes on the Proverif model. If the crypto changes, then on the SS proof model or so on. Yeah.
Question. In fact, Signal is the perfect answer for this, because in Signal there is actually like a one person, really maybe two people sometimes, who do the protocol design, and it's always been like this. It's an important protocol, but one or two people do it, and then there is like 3 or 4 people who do the implementation. Okay, and the 4 people doing the implementation are less expert, I would say. But so the designers directly want to write Proverif. They enjoy writing that, so they've gotten hooked, let's say, like many of us have, right? So for that it works, right? So because then, yeah, they would actually go and actually write the Proverif, re-verify it, verify the properties that we together came up with, but they would re-verify it. And if something fails and they don't understand it enough, they might ask us or Bruno or somebody else who's an expert, saying, hey, can you help us? But they're willing to use the tool directly, right? But the reason for doing the hacks thing is different, actually, because they are worried that during the implementation, they may have, because they have a fairly complex state machine, they may have messed up something, so that in fact the protocol as implemented is not exactly the protocol as they designed. So there are 2 choices there. You can either prove conformance between these two, but doing conformance between distributed programs is kind of a bit annoying. So rather than doing that, we say, hey, you know what, just directly do the verification again on the code. So it's kind of a different verification. It's more like sanity checking. And you're right, the model that comes out of there is not nearly as nice as the one you can write by hand. But we try to make sure that the same properties are proven for that as well.
Yeah. So have you tried to do any of this verification effort with Dafny', or is there a comparison you want to make between the capabilities of Dafny' and F-star? Yeah.
So of the work that I showed you, Veil has been used with both F-star and Dafny'. And if any of the Veil people were here, they could give you a hi, yeah, of course. Right, sorry, you guys can give a proper comparison maybe later on as part of your question answer. But we primarily use F-star. I have some experience with using Verus for similar things, which again has a similar feel, let's say. But I can't speak specifically to Dafny'.
Maybe a related question because about this F-star, because my understanding, like I don't really know what it does, but like it's proving functional correctness for you, like type of properties. So like why, like presumably you could prove some of the same properties with Verus directly or with other like SMT based tools, like so. And like what actually, can you just, for us who don't know, start brief summary of F-star and what?
So Hacks has a different kind of philosophy than Verus, in that rather than using the one true SMT solver pathway, we are a bit agnostic and we say, hey, you can use any number of tools. We even have a lean backend, we have a rock backend, a star backend, and then on the security side, we have an SS proof and a Proverif backend. People are interested in building other backends. So the idea is, depending on what proof you want to do, you can write the right annotations and guide it towards that tool. So some of the proofs that we're talking about, like functional correctness, you can definitely do with Verus. You can also do with Eneas, which is a tool by Sean Ho and Jonathan Podzenko and so on. And they're kind of close collaborators of ours. So there are many tools, even Crezo, whatever. You can do these functional correctness proofs there. There's the panic freedom proofs that, again, all of these tools can do. We have nice comparisons between all of them as well. But here, we are primarily focused on the crypto side of things. And there, we want to interoperate with things like Hacklestar, with some other kind of, there's a whole framework called device star for doing security proofs in F-star. And there's a whole bunch of these things which already exist in F-star. So for us, being able to interoperate them with them is valuable enough that we go to F-star. But if you were willing to re-implement all of these things in any, like in Lean or in Dafny' or in whatever, then yeah, we could go that way.
I have a question on the transition to PQC. So there's a number of companies now offering the services to deliver PQC-ready libraries, crypto libraries. And so you do that too. So in competition with them at Cryspen. And some of these other companies, they also use formal verification, but very few in fact. So PQ Shield, for example, uses some formal verification. But most of these...
So I can't tell.
They advise that, they advocate for that on their blog, but yeah, we don't have the source code. But for sure, most of them don't use formal verification. And so how do you see formal verification really making a dent here? Like you said, that's an opportunity. How is it going to materialize? Do you see other players than you pushing for that?
So, in fact, PQC is, we did our work on LibCrux was funded by Google, and the idea is that hopefully Boring SSL will adopt the code that is coming from us. But it's still an open question. I know for a fact that Microsoft is working on its own SymCrypt, formally verified post-quantum crypto library. So they're going to do that using NAS. They are doing that. Maybe have already done a chunk of it. AWS LC uses a combination of CBMC and Isabelle to verify their post-quantum crypto. So Apple is not making too many noises, but maybe they will also have formally verified crypto in the future because they've hired some formal verification engineers recently. So I can totally imagine this becoming like the default, actually. So when we are trying to tell people to use our library, we don't actually sell it. It's open source. We don't believe that formal verification should be a selling point. I think it should be the default. Right? So what we give to Signal, for example, why they use LibCrux is that in their new protocol, they needed a new API for doing MLChem in a kind of a novel way. It's actually interesting in that MLChem braid. And we were able to implement and verify this new API for them and deliver it to them. So I think the functionalities are what we should be pushing, and formal verification should be default. It's not yet the case, I agree. But I don't see a future in which people should be using non-formally verified code. Of course, you also need testing, you also need FIPS certification, you need a bunch of other things, but this should be the baseline, I think.
Hello, nice talk. I want to ask a silly question. So, do you expect like artificial intelligence, like large language model, can mitigate the proof effort of cryptography? Because I assume so what I understand is that the proof effort of cryptography, like for TLS, is really, really huge. But do you think there is a chance, or like how much effort can be saved with the help of large language models these days?
Good question. I don't have an answer, but there's a whole bunch of people working on it. We are also investigating that. And it's unclear. I think there is a whole bunch of things like deriving annotations or propagating annotations that we do a lot of manual effort on, which should really not be done. And I use LLMs to automatically propagate things now. Ultimately, I believe that there should be a trusted proof checker that shouldn't be based on LLMs or AI, that can actually check the artifact that's coming out. And the way the artifacts are generated, you can use, whatever techniques that you want. And I think there's lots of people working on, like, you give me a big lean file full of sorries, I'll fill it up with proofs, right? And this is kind of a very common pattern, right? So that people are working on. And you can imagine the same to be done for large systems like TLS. I have not yet seen results that have shown that this is actually applicable at that scale, but it wouldn't surprise me if a lot of the proofs are automatable, not automatable, but fillable, let's say, using LLMs, and then should be checked using tools like the ones shown here.
So thanks you, Karthik. We'll have to stop here for the sake of our strict schedule. Thank you.